name's Donovan Jones, but you can just address me as Mr. Jones. First thing to get off my chest, I am sorry about the quality of this video. It's probably atrocious, and I'm probably jumping all around the screen right now unless I move like this. But that's due to the fact that I'm running this on a decade-year-old laptop. But anyhow, the rest of the video won't be like this. It's just an upfront apology about it. Anyhow, I'm doing this for a grade for my Chemistry 325 method lesson plan project. Essentially, I went into a school and I taught a quick lesson, but now I'm really getting into the topic, I say, and actually making a lecture surrounding the material I taught, and which, of course, is going to be solutions as well as concentrations. Now, I've broken down solutions into three main parts, that being their actual type. So whether it be solid, liquid, or gaseous. These will, of course, be covered in the next 50 minutes. But also, I broke concentrations down into a very similar subcategory by type, meaning I'm going to present mass percent, volume percent, mole fractions, and molarity, all in their own little categories, each with plenty of example problems so that you, by the end of this, can know how to do just about everything concerning solutions and molarity. Well, that's about it. Let's jump straight into it.
Hi. As you can see, the video is no longer choppy, and I did manage to keep my promise. Now, as I said earlier, we're just going to hop straight into it. See, solutions was a homogeneous mixture. Mixture of two or more substances and exists in a single phase. Now this is the definition for solution. Further on, a solution can be classified further on as either binary, tertiary. It all depends on the amount of substances going into said solution. So, for two substances, the solution will then be called a binary. Well, for three substances, the solution will be called a tertiary solution, and so on and so forth, quaternary and whatnot. In a solution, let's say it's a binary solution, there will always be a solute and the solvent. See, the solvent is going to be the larger proportion of the two. Doesn't matter whether it's a solid, liquid, gas, whatever it may be, it is going to be the largest proportion. Meanwhile, the solute will stand to be the lesser proportion. Now, a lot of questions are going to ask you what kind of phase the solution is going to be. And the phase of the solution should always match that of the solvent. Same phase. So, let's say the solvent is gaseous. That means that the solution itself will also be gaseous. So, again, a binary solution contains just two substances. the tertiary, contains 3. The solute will always be the lesser proportion within that solution. Meanwhile, the solvent will always be the larger proportion. Now, let's practice a couple examples of this. All right, let's say there's 5 grams of sodium chloride, just simple table salt. It's soluble in water. So let's say you have 100 milliliters of water. By mixing these two, you're going to find that you get a liquid solution. And of course that is because the solution is in liquid state, ergo water should be the solvent. As sodium chloride will be the solute. Let's say now we have 1,000 grams of sodium chloride plus only 50 milliliters of water. If you still have a liquid solution, your solvent is still the water, despite the fact that it is the smaller proportion. It's sort of a law that trumps the previous we just talked about. Now, based on the phase of the solution, you can further break down solutions into 3 types. That being solid, liquid, and gaseous. Now, the solvent in a solid solution will of course be solid. However, the solute can be anything. It can be solid, liquid, gas, whatever it needs to be. This stands to be the same in both liquid and gaseous solutions, as the solvent will need to be homogeneous with the solution. Meanwhile, the solute, what's being mixed in with the solvent, can really be just about anything of any different state, as long as it still combines to form a homogeneous mixture. This results in us having about 9 different combinations. Solid and solid, liquid and solid, gas and solid, and so on and so forth. Solid into liquid, liquid into liquid, gas into liquid, and further on, if solid into gas, liquid into gas, gas into gas. But again, the real overarching point of this is that the phase of the solvent should always match the phase of the solution. Now, through these 3 solutions, we're really just going to focus on liquid solutions and the upcoming problems that we're doing. For this lecture, we're really going to just study liquid solutions instead of both gaseous and solid. Within liquid solutions, there's plenty of different kinds of concentrations to choose from, but mainly how we're going to divide them is between those that are temperature dependent and those that are temperature independent. Temperature dependent concentrations are things like mass over volume percent, volume over volume percent, and molarity. As you can see, these are due to the fact that within these concentrations there's a volume present. And as you know from previous chapters, volume is directly dependent on temperature. Meanwhile, temperature independent concentrations will be things like mole fractions, percent mass composition, and things like molality, as well as normality, which we won't be talking about in this lecture. Now, mass by mass composition is fairly easy, as what it really is the mass of solute over the entire mass of the solution. Meanwhile, mass over volume composition is essentially the same thing, except you're still taking the mass of a solute. But this time, it's the volume of the solution. We'll practice these two relationships later on when we get to our practice problems. The next concentration we're focusing on is mole fraction. This basically represents the percentage of one mole as opposed to another when looking at the substances within a solution. So let's say we have moles of X1. Well, say we have substances, right? X1 and X2. Each being entirely different substances. If we wanted, say, the mole fraction of X1, we would take the number of moles of substance 1 divided by the number of moles of both substance 1 and 2 in this binary solution, resulting in the mole fraction for our first substance. This could be easily switched out and just done for X2, which would be substance 2, as seen right here. Now, X1 and X2 will always combine to reach 1 exactly, making it a fraction. This can be easily implemented when you're doing even a tertiary system. So we throw an X3 into the equation, meaning that we're just looking at the moles of the third substance divided by N1, N2, and N3. Now, as a quick refresher, to find the moles of any substance, all you need to do is take, let's see, the grams of the substance divided by the molar mass of said substance to give you moles. This can be quickly calculated for just about any of our future examples that we're going to run through. Molarity is it's not impartial, sorry. It's a very important concentration, as it's used as a standard for most chemical equations you'll be doing. Now, molarity is also temperature dependent, but it's tracked as moles over volume. Now, I know it's quite hard to see, but these were various whiteboard presentations I captured during my method lesson reflection plan that I thought would really demonstrate molarity quite well here. See, in my lab, the students didn't know what they were really finding, right? They just knew that they had a certain amount of grams of sugar and a certain amount of volume of soda, right? And so that graph there you can see in this upper left-hand corner is that moles charted against the liters. And as you now know, moles, of course, over liters is molarity. But I just thought these were a really good demonstration of, I don't know, how you could potentially teach kids the correlation between moles and liters. Another important distinction to make before I can really crack into the practice problems here is how to work with density. In a lot of questions, you'll see density brought up as either grams over milliliters or even grams over centimeters cubed. In this regard, you can obviously see that milliliters are almost interchangeable with centimeters cubed. And this would always trick me up on my own problems, but they are interchangeable in any sort of way. Another quick reference for later on is that 1 liter is equal to 1,000 milliliters, and vice versa. 1 kilogram is equal to 1,000 grams. For the first problem, we'll do a nice and easy mass percent problem. So let's say we have 25 grams of NaCl, just common table salt. We dissolve it in 300 grams of water. Now, if you remember earlier, the solvent will always have the same phase as the solution later on. If this is an aqueous solution, we know for a fact that this water here will act as our solvent. But anyhow, what is the mass percent of the solution? So right from the start, we can remember that the mass percent is equal to the mass of solute over the mass of the entire solution. This will, of course, give you a decimal, which you'll later have to multiply by 100 in order to really turn into that percent. So, simply, we could just take 25 grams of NaCl and divide that by our 300 grams of H2O, timesing it by 100, Oh. See, I made my own mistake at first. I did the solvent rather than the solution. See, the solution is in fact the solvent plus the solute, meaning that instead of 300, it would be 325. This will end up giving us a mass percent of about 7.69%. For the next problem, we'll make it a bit more of a two-parter. So let's say we have this time 37 milliliters of, let's say, methanol at a density of roughly 0.843 grams per centimeter cubed. This is going to be mixed with about, let's say, 200 milliliters of water. Density being, let's just say 1 gram. 1 gram a milliliter. First off, we're going to try and find what the volume percent of methanol is. And then afterwards, what is the mass percent of water? So first off, volume percent, as we know from our little previous talk, is just the volume of solute over the entire solution. Not just the solvent, like we did earlier to my mistake. Timesing it by 100, again, to get that actual percent. Now this is pretty easy. We're just going to do 37 divided by 237 milliliters, of course. And that will give us roughly 0.156 times 100, of course, giving us 15.6% methanol. Now that first question was quite easy, so we're going to move straight into mass percent. Just like the last question, it's going to be mass of solute over the entire mass of solution. But we're not really given the mass straight offhand, right? That's where we have to remember our density equation. D equals M over V. Except this time we're just going to be finding M, right? So by switching this equation around, we're instead going to make it M equals D times V. Easy enough. So for methanol, we're just going to straight up take 0.843 grams per cubic centimeter. Switch this directly into milliliters, since as we saw earlier, centimeters cubed can strictly just turn right into milliliters. And then we're going to multiply this by the volume of methanol we have, meaning 37 milliliters, giving us a mass of 31. I realize I'm just off the page a little bit now. Of 31.191 grams. We can do the same thing here for our water, as we take the original 200 milliliters we have and multiply it by our density of just 1, meaning that we have exactly 200 grams of water in our solution as well. Now, remembering those numbers, we'll switch it to the next page. Methanol and 200 grams water. Again, finding the mass percent, quite easy. We're taking the solution, which will be 31.191 grams, plus 200, all dividing the original 31.191. Wait, did I ask for methanol or water? I'm sorry. We asked for water instead. So not the 31.19 grams, but rather the 200 grams present in the water. This will give us a mass percent of roughly, calculating it out now, uh, 0.865, which we know by multiplying by 100 will make it 86.5% mass. Next, we'll do just a nice little mole fraction kind of question, right? So we'll start out with NaCl, our old friend table style, as we saw in the previous questions. And we'll just say that there's 3 moles. These moles are dissolved and around 12 moles of water. It's supposed to be an O there. What is the mole fraction of both? Now, if you remember from our little explanations earlier, our substance, let's call this X NaCl and X H2O, are both just going to be like our mass percent in a way, taking the moles of our substance and then dividing them by the entirety of the solution. So the 3 moles plus the 12 moles, obviously. So X NaCl plus NX H2O, meaning it's just going to be 3 moles H2O divided by those same 3 moles with the addition of the 12 moles of water. Sorry, this is meant to be sodium chloride. And again, that should just give us a mole fraction. Of 0.2. God, my pencil lead just keeps breaking on me. Meanwhile, we know that this 0.2 will add up with our second substance, H2O, to equal 1. So we can automatically assume that our molar fraction for water will be 0.8. But just to run it through, we'll just do the equation real quick. 12 moles divided by 3 plus 12 equals 12 divided by 15, exactly 0.8 moles. Now in this next problem, we'll just try something a little harder. So for this next equation, instead of giving the exact moles, we're going to start off with the grams first. And as you know, we'll then switch through the molar mass to moles and finally find out the problem. But in this instance, we're going to have, let's say, 40 grams of that NaCl we just used. And now this is going to go straight into 300 grams of H2O. And we want to know the mole fraction of each. Well, first, obviously, we're going to take these 40 grams, take the molar mass of those, of NaCl, which I believe, just some quick mental math, is about 58.4 grams per mole. With that equaling out to 1 gram, or 1 mole, my bad. That'll give us exactly 0.684 moles of NaCl. Meanwhile, for our H2O, we're going to take that 300 grams divided by its molar mass of around 18.01, giving us 1 mole, and thus end up having a much larger amount of moles, somewhere in the area of 16.7 moles. And then after that, it's as simple as doing exactly what we did last time, and taking the moles of NaCl, 0.684 moles NaCl, and dividing it by both the 16.7 moles of water and the original 0.684 moles NaCl. This gives us a rough mole percent of 0.04%. Meanwhile, that means that water is going to take up a whopping 0.96 mole fraction. let's now work on molarity question then. So we'll say we have, again, 30 grams of sodium bromide, right? And this is dissolved in a 200 milliliter solution. What is going to be the molarity? So, from our previous talk, we know that molarity is going to be moles of solute over liters of solution. So, we need to get from grams to moles for our solute, and then also convert over into liters from milliliters. So first we'll start with just our simple milliliter to liter conversion. So we know that there's about 1,000 milliliters in a liter. So 2,000 milliliters to 1,000 milliliters over 1 liter. Easy enough done, resulting in 0.2 liters. Easy peasy. Now our 30 grams of NaBr is going to have to get taken by the molar mass, which here we can just add up real quick. So let's see, 23 for sodium, we'll say 79.9-ish bromide, giving us a whopping total of 102.9 grams per mole. Excuse me. Now this molar mass we just found, we can take it immediately. One mole. And find out exactly how many moles we're introducing into the solution. Now if I just do some quick math, 30 divided by 102.9 will give us a rough mole estimate of 0.291 moles NaBr. And now we kind of have all we need, right? So we can just put our moles over our liters of solution to give us a molarity of a little bit bigger than 1, almost, probably around like 1.5. 0.291 divided by 0.2, giving us 1.45 molarity. Now, I know I said we wouldn't really touch on it, but I thought it'd be nice to do at least a little bit of a molality problem. So just like molarity, it's quite simple. Molality, instead of having liters of solution as its bottom denominator, instead we'll have kilograms of solvent. Meanwhile, the moles of solute stay the same. So in this question, we'll say we'll have 17 grams of, say, sodium hydroxide, and it gets dissolved and 250 grams of water. What is the molality? you can already see where this question is going. First, we're going to find the molar mass of sodium hydroxide real quick. So taking the sodium, the oxygen, and the hydrogen, by adding them all together, about 23, 16, and 1, we'll get a 40 gram per mole molar mass. Of sodium hydroxide. Now taking the 17 grams we're using and finding out how many moles is in it. So dividing it by 40 grams per mole. 1 mole will give us a mole content of roughly 0.425 moles NaOH. This gives us, obviously, the numerator of our big problem that we're going to need. Now, kilograms is solvent. That isn't too hard to remember. As earlier, with my little references, we remember that 1,000 kilograms, 1 kilogram is equivalent to 1,000 grams. So by taking this 250 grams that we're actually using, and throwing it through a little bit of stoichiometry to get our kilograms. And this lead is terrible. We know that we'll have about 0.25 kilograms of solution. Now, taking those moles of sodium hydroxide and dividing them by kilograms of solution that we have, or solvent, sorry, we know we'll get roughly about 1.7, thus giving us the molarity of this little problem. Okay, now for this question, I thought we would do a little bit something more comprehensive to everything we've been doing so far. So I'm thinking we start out from a given mass percent with a given density, and then by combining those we'll move on to something, we'll find a molarity. Right? So let's start out with our good old friend sodium chloride, table salt of course. Let's say it has a mass percent of 23%, right? With a density of, let's say, 1.12 grams per milliliter. What's going to be the molarity? Now, it may be hard to really start this off, but what we're going to do is just work it piece by piece, and eventually we'll get to a starting place that looks a lot easier to finally solve the molarity. So we know by the formula for mass percent, that's going to be the moles, mass of solute over the mass of solution. Course times 100, right? So then, easily enough, let's say, to get that 100%, we could easily say that the mass of solute is just 23 grams of sodium chloride over that 100 grams of solution, right? That divided out gives you 0.23 times 100, 23, bam. So then, if we can move this on. Sorry, I'm working it out in my head to find here. I'll just transfer this to the next page. We remember that molarity, not molality, is going to be moles of solute over liters of solution. So already we're getting pretty close to our solution, right? Let's take this 100 grams. Wait, did I do 100 grams? See, this is the problem with these questions. I did. Ha ha ha. I did forget the density I made up. It was 1.12. Bam. So that density becomes important here as we find out that 1.12 grams basically give us 1 milliliter. And then if we want to take this even a step farther to just jump straight to liters, we know that 1,000 milliliters goes into exactly 1 liter. So then we're going to find our entire volume of solution quite easily. And it'll end up being something around the ballpark of, let's calculate this out, 100 grams divided by 1.12 plus 1,000 equals 0.0999 liters. Yes. Sorry, I had to double check my work. And then we can take our 23 grams of sodium chloride and find the molar mass again, of course, meaning dividing sodium by chloride. Here, I have it written down here for easy access. It's just 58.44 grams per mole. So then with that equaling 1 mole, that would give you 0.394 moles. And now, since we have our moles of solute, which is 0.394 moles of sodium chloride, and we have our liters of solution being 0.999 liters, we can find that our actual molarity for this equation is going to be 0.394 moles divided by 0.0999 liters, giving us a molarity of 3.94. Thank you for watching. I hope you learned a little bit, whether it was the definitions of solutions or concentrations or the various different kinds of solutions and the various different kinds of concentrations that we went through, or really just any of the practice problem work that we went through, from the molar ratios to the molarity problems. I hope you at least learned something. Have a good day, and thanks for watching.